Good day, everyone. Welcome to another virtual DDD meeting. And with me is Christina from the organizers. And today we are honored to have Grady with us, talking about 50 ways to scale your Agile. So if you're on YouTube, just chat away, ask questions, and we'll try to ask them live. And similar goes to the ones who are on Zoom. And well, happy to have you with us, Grady. Thanks for coming.
Delighted to be here. Shall I begin?
Yeah, please. Go on.
Okay, let's do it. Let me see how I share. Just a moment.
Yes.
There we are. And let me set things up so I can watch the chat simultaneously. So, okay, so I'm seeing the chat. I think you can see me.
Yep.
Very good. So let me make this bigger because we're going to be settled in for a while. All right. I am infinitely accessible. Here are the ways you can reach out to me. My email, follow me on Twitter, website that I'm on. So seriously, I answer all my email. I tend to strive toward inbox zero. So I'm relatively responsive to any questions or things that you may have along the way. Let's begin with the thought experiment. And let's start with a happy place. Imagine the most successful Agile project you've been with. Sort of get it in your mind, feel how it was, imagine the flow, and now begin to imagine the size. What was the size of your team? What was the duration of your overall project from the time you began till you went into, final production? What was the complexity of the system that you were building? How many lines of code, if you want to go that way? Now pause for a moment, sort of get it in your head, feel good about it. And now think about the largest project you've been on. May or may not be the same thing. If it's the same one, then good for you. You are in a wonderful place. But it may not. Imagine, too, the number of people involved. Imagine its complexity. Imagine the struggles you felt along the way. Imagine, get in your head how long it took you to actually do a release. And think for a moment where the points of friction were. So get that in your head. Now, take that size of that project and double it in size. No, that's too easy. Increase it in size by a factor of 10. That's not enough. Increase that in factor by a size of 100. And imagine for a moment a project of that size, magnitude, risk, complexity. And consider, how would you take those things that worked in your happy place and apply them to the larger thing? You may say, not even going to try. Or you may say, well, it's easy. Well, this is the situation I face. I've been involved in my career in hundreds, if not several thousand projects. Everything from working with the London Underground to the early days of Facebook, to banks, insurance companies, satellites, you name it. I am currently on the largest project I have ever been involved in my career, and that's therefore saying something. I can't tell you what it is. You may be able to make some guesses if you do a search, but this particular project is budgeted at $100 billion for development. It's a hardware project, software project too, but it's a software intensive one. And its development is expected to last roughly 5-ish years. But then its operational costs will be somewhere on the order of $250 billion. Its expected lifetime is literally a generation, 50 years. Indeed, the current system that it's replacing has already passed its expected time, and thus the urgency to do this. It's about 50, approaching 60 years old and needs to be replaced. It has hard real-time as well as non-real-time elements. So when I speak of hard real-time, it means you slip a bit and things go awry. Indeed, failure in this particular situation has civilization level consequences. This is the reality of the project on which I'm in, and we're attempting to apply agile methods to it. So we'll talk about this a little bit along the way. I'll offer some other war stories, but this is agile at scale. And it is indeed a challenging one, but I'm happy to report it is indeed possible. So you may say, wow, my development team should look like this. I won't tell you the name of this company, but this is your typical Valley project. People crammed into the same room, different monitors, different kind of machines, yada, yada. A typical physical workspace pre-COVID for development. When I first picked this picture up, my first reaction was, wow, this is fascinating, but there's something really interesting. I want you to stare at it for a moment and see if you can see the same thing that I saw along the way. Is it, different machines? No. Is it the open office? No. Is it the funny decor? No. My reaction was, where did they hide the women? Well, that's another lecture unto itself about women in computing. I'm not going to go there. That's not the topic of this discussion, but it, of course, is a very real issue as well. I was also worried about this screen in the upper, in the lower left corner. It's like, whoa, that's kind of a funky orientation. At any rate, you're not going to apply a project like this and expect it just to scale instantly to the problem I described. So how do you do that? How do you bridge the gap? As I said, one possibility is you just don't do it. I pose this to many people and say, hey, just apply your same approaches. They said, well, no, it's not a simple matter of programming anymore. It really, really isn't. And so some people say, don't even try it. Well, that's not an option. That in a small world, you may say, I'm refusing to do that. That's fine. That's your personal choice. But there are needs of organizations, there are needs of governments, there are needs of nations, there are needs of civilization that compel us to build these larger and larger projects. Then you may say, well, break it into smaller agile projects. Well, yeah, but that seems like the most intuitive things, but realize all you've really done is shift the levels of abstraction. And so the same kinds of dynamics are playing a role here. So what I want to do, therefore, is let's explore this. How do I scale my Agile project? How do I scale my projects? And how do I keep the goodness of Agile along the way? And honestly, it's this. Use system engineering best practices, which is why we call them best practices. Now, quick aside, I'm offering a little bit of a slam to a certain book about software architecture that claims there are no best practices. We have agreed to disagree on this matter because my experience is that there are some best practices, and they are called that because they have proven to be effective over the years. But this is sort of the essence of my talk, that yes, it's possible to scale Agile. Be careful about following into cargo cult thinking, as we will talk about in a moment, but it really is a matter of falling back on these essentials. Let's remind ourselves of the roots of Agile programming, and the context is important. Kent and Ward, two of my heroes indeed. And Kent, of course, working together with Ward in some of the early days, I think it was at Chrysler. But it was that experience that led them to some self-discovery about how it was they built systems in a very efficient, wonderful fashion. But remember the context. They were building systems that were relatively novel in their time. Here we are at the cusp of the web, the beginnings of the web, user interfaces. We're really just in quite flux as we move toward web-centric kinds of things. And the very nature of interaction with individuals to these systems was in flux as well. So they were, and also I would add, they were dealing with, by the standards I just described earlier, relatively small systems. So what they developed and what became XP is quite understandable in that context. And I too, by the way, love Kent's practices. I think he was doing some tremendous things, and the idea of test first development is absolutely spot on. And by the way, it scales as well, as we shall see. But the practices they came up with were very much from a context of smallness. And that's great, because there are a large set of problems that fit that particular profile. Well, move ourselves forward several years, and you'll see that the folks who built up the Agile Manifesto had a number of those concepts in mind. And I think it's important to reflect upon these, because if you look at some of the Agile methods at scale, I think they forget some of these principles, and they have focused too much upon the ceremony and ignored the principles. Because if you think about them, virtually every one of these principles even apply to systems at scale. I tweeted late last night in a fit of desperation / inspiration that there's a litmus test I use when I can distinguish a successful company from one that's on failure. And it's the questions they ask. If they're asking, what do we need to do to delight our customers, versus where do we get the next $1 billion in revenue? These are fundamentally different questions. And the former suggests an attitude of caring about the customer. That's great. And when you care about the customer, much like Kent and Ward recognized, you realize they don't know even what they want at the very beginning. And so you have to be in partner with them to help them understand and help you understand what it is you really need along the way. And these notions of delivering software frequently and focusing upon executable code, this is just basic engineering that all of engineering, if you look at it on a global historical scale, you realize it is exactly that it is a process of self-correcting along the way. And another thing, last two things I'll mention on this, is that you can't ignore simplicity, but simplicity is really, really hard. And as I increase ceremony, it tends to fight against the desires for simplicity. Now, reflect upon this last one. The best architectures come from self-organizing teams. In your happy place, I think you found that to be true. And as we'll see in a moment, turns out that this is historically true as well. Well, see, I'm hitting the wrong button here. There we go. So even in the presence of scale, my experience has been these principles hold. But as I said, methods have become a bit of a cargo cult. We see certifications left and right, bless their soul to the people trying to do them. But, I understand why, and I understand the economics of it, but be careful, because you end up, like all sorts of even religious fundamentalism, you start worrying more about the rules than you do about the principles. So be careful along the way. So I said, these ideas have a long history. And in fact, let's spend some time here looking at how we dealt with scale over the ages. Wow, in this one, they didn't hide the women because they're right in front and center. This is a great example of a self-organizing team that's incredibly effective. You may not know this history, so let me spend a little time on it. This happens to be Harvard in the second half of the 1800s. And these were Harvard's computers, literally computers, because back then computers weren't things, they were people, and most of the computers were women. In fact, these are Harvard's computers. There's a gentleman standing up in the back. His name is Pickering. He was the lead astronomer at the time. And these are the computers that work for him. So if you think about it, this looks like your classic Scrum stand-up. And in fact, this is how these folks worked. That the astronomers would say, hey, I've got this data, go munch it and, give me these particular results from it. And so the women, the computers, would go off and do it. They were your classic self-organizing team. They were given no direction. They just said, give us the results, and they found themselves how to organize. The woman in the front is particularly interesting. That's Annie Jump Cannon, the one with the magnifying glass. And she's of particular interest because she was sort of I guess you'd say, a leader of the group in one way. And the things she discovered along the way about how to measure luminosity of stars are techniques we still use today. So this is your classic first self-organizing team. Oh, there's one other aspect I should mention. Back in the day, it was viewed that the work these women computers were doing was beneath the men. And so the men would devise, this is what we want done, and they'd throw it over the wall to the women because it was the menial stuff the women would do. But nonetheless, as we realized, it was the self-organization of those teams that led to quite success. Same story repeated itself as we move forward a century or half a century, 3/4 of a century, toward the end of World War II. What you're looking at here is the Eniac. And the Eniac went through exactly the same kind of social organizational phenomenon. So here we had a machine, an electromechanical machine, originally devised to deal with the tedium of ballistic table management. Later on, because it was a little bit late in the war, it was used to do nuclear weapons simulation associated with the follow-on to the Manhattan Project. In fact, let me go back in time. Richard Feynman was the great physicist who was involved in the Manhattan Project. He, much like Pickering, led a number of women computers primarily during the work of the Manhattan Project to do almost exactly the same kind of style as what we saw Annie Cannon do. But here, back in Eniac, it was the same kind of thing. You'd have the mathematician saying, hey, here's an algorithm, go off and implement this thing. And they would throw it over to a handful of women who would say, okay, that's cool. And these women were very, very close to the machines. In fact, it was this group of women who wrote the operating manual for the Eniac, which, by the way, go to Amazon, you pick up a copy today. What was the nature of programming back then? It was the plug boards. This was not a stored program computer. The programs were in the plug boards themselves, and it wasn't later until it became a stored program thing. And so what you find happening is the women self-organized, just like in Pickering's group. And here's the other important thing, they began to discover common patterns. And they would reuse those programming patterns again and again in their plug boards themselves. Go visit the Computer History Museum. They're on the web, obviously, and there are a number of oral histories of 5 of the women involved in the Eniac's work, and it's quite interesting to see how it evolved over time. Well, the world changed as we moved toward the 50s, 1950s, 1960s. What changed? There were some technological ones, there were some economic ones. The technological ones were all of a sudden, we had far more powerful machines, and the kinds of systems we were building were far more complex. But for the most part, the systems we were building were the automation of existing processes, the automation of the stock market, the automation of accounts payable and receivable. These were the dominant things going on. The economic element was our machines cost more than the programmers. And therefore, no surprise, methodologies rose because they tried to optimize for the needs of the machines, not the needs of the programmers. So, don't condemn them for the time because the methodologies that emerged, this is really the first generation of software engineering methodologies, was absolutely appropriate for its time. And it was a time that we call the programming priesthood. And it was very waterfallish, and rightfully so, because of the economic issues. We'd established our requirements. Analysts would go off and work with customers. We'd translate those into algorithms. The programmers would take those, write them up on flowcharts and reason about it for a while. And they do this offline because the machine costs were so high. They'd eventually write some code. They'd pass it over to people who would key punch it, which, by the way, the women were now pushed from the roles of programmers for the large part and moved to typists, which is an interesting story. Go read the book by Mar Hicks on the phenomenon in the UK in particular, and you'll see that whole story there. But it became a relatively rigid life cycle, and it was right for its time frame because of the nature of risk, the economics, and the complexity involved. But again, the world changed as we moved toward miniaturization, not just first mini computers, but then microcomputers, because all of a sudden we were becoming a little bit more on parity with the human and the machine. And that enabled much more rapid feedback. Back in the days of the 360, you might deliver a job in the morning, get results later in the day. If you're lucky, you might get a few runs during the day, but it just didn't work to enable to have rapid feedback. But mini computers changed that role, and microcomputers changed it as well. The other thing that happened along the way is now all of a sudden we were dealing with a new set of application domains that were no longer old ones, not just replicating things we'd done before, but opening up an entirely new dimension of things we would like to build. And so the architectures of what we were doing were changing as well too. Of course, the world changed even further when Sir Tim evolved the web, and then changed even further with the advent of mobile devices, because all of a sudden we had fundamentally different ways in which to interact with our systems. Where we've been headed, of course, is toward this, where you see devices that have bits of software in them everywhere in the world. I did a quick count on this once, and there are at least several hundred automated devices in just this one picture. And we're moving to this direction. This is a shot of Copenhagen. I tried to find a shot sorry, the name just popped out of my head, of another country, Estonia. There we go, Estonia. Because Estonia is particularly interesting. They are perhaps the most digital country ever. And the phenomena is we are seeing software move its way into the interstitial spaces of our world. And so now the stakes are changing as well, because it's no longer just replicating something we've already done or building something novel, but now we're building things that impact the livelihoods of individuals, the livelihoods of organizations, the existence of nations and civilization itself. And so the stakes are quite higher indeed. We're going to spend a little time at the end talking about this, because the world is changing. I would imagine most of you are working in the domain of symbolic systems, classic programming kinds of things. But we're moving into a realm of where AI becomes more and more a part of what we build. And at the end, we'll even talk about where quantum fits in, because these are beginning to impact. So the question you may ask yourself is, how does Agile apply to artificial intelligence systems? And I'll tell you what we discovered along the way. So if you look at your classic web-centric system today, it looks like this. And I need to explain this a bit. The connected things in the background, the green and the whitish stuff, all the network things, that's classic web. And that's sort of the plumbing beneath everything here. You see with the little blue squares and such, there are one-offs, well, not one-offs, but actually billions of devices on the edge that exist out there. But you'll notice these circular things with the pixelated stuff inside. Here's what the economics of the web has led us to do. It has pushed more and more people to the cloud because of the economics of on-premise versus cloud storage, which, by the way, the pendulum keeps swinging back and forth. But it also has given the rise of microservice architectures, where organizations have realized there is tremendous economic incentive, there is value to our customers, there is value to how we deliver our software systems to build things up in a microservices style. And in a moment, I'm going to give you some war stories on these, but this is sort of the classic architecture. So the lesson here is be careful, because when you read stories about Agile, when you read stories about, oh, here's how I do architecture, remember that most of it is applying to this domain, but this is not the only domain in the world. Let's do some war stories here. War stories primarily about projects I have been engaged with that have been using Agile successfully or have tried to use Agile successfully. The IRS, the Internal Revenue Service, the place in the United States that we gladly pay all of our taxes to. I have had the opportunity to spend considerable time with the architects at the IRS, because they have an interesting problem. First off, it's a huge computing problem. They're dealing with the tax returns of, several hundreds of millions of people, countless corporations, and the influx daily of data that comes in. But they're doing so given a changing tax base. They're doing so changing tax rules, and they've got to release this, every year. You can't just shut it down and say, hey, wait for us for a while. So there's been this problem of continuous evolution, and there is considerable technical debt within the IRS. So there are attempts to apply Agile approaches, but it's really hard when you're dealing with this large, massive legacy. I would say the IRS has been successful in applying Agile in the small, but they have been widely unsuccessful in applying it for large transformation. I was amazed to find out that at the very bottom of IRS's tax systems, there still exists, well, I'll ask this question: what language do you think it's written in? Most of the code. You may say, oh, it's COBOL or it's Fortran. No, it's not. At the very bottom of it is IBM 360 assembly language. There is still assembly language at the bottom of this. So imagine the problem of taking an Agile team with that legacy, and you can't fail. It is indeed hard. Amazon is exactly the opposite of this. And the lesson here is the importance of a strong architectural vision in the presence of Agile teams. So in the earliest days, Bezos, being who Bezos was, said everything shall be a service. And his developer said, no, we don't like that idea. Because remember, this is the earliest days of services. We were back in the time of even early SOAP, the Simple Object Access Protocol from Box and others. And so it was an unknown idea, but he took a risk and said, no, it shall be so. But because of that architectural decision, they were able to build up an infrastructure, and they went through several times of it internally, that enabled them to build up a set of services that would let them say, hey, we could now take those services and allow other organizations to build up their own stores. It looked like it was Amazon, but they were really running it. And so the idea of an Amazon store was born. Similarly, they realized, wow, we've got all these services associated with our infrastructure for the cloud. Why don't we peel those off and sell those as well? And thus was born Amazon's cloud, AWS. It all sort of followed through because that one architectural decision that was reinforced and developed by Amazon's Agile teams. So what's the lessons here? Agile works at scale, but it requires a strong and consistent architectural vision along the way. Salesforce is a different beast. I've had a chance to work with people both inside and outside of Salesforce. And they are perhaps the first company that really pushed software as a service and the idea of all these microservice things. And that was great because it enabled Salesforce to begin to divide up its organization, its development staff, into lots of small teams. But remember, you still had the need for an overall architectural vision because the outside customers wanted to have a unified vision. From the inside, Salesforce wanted to optimize development by small teams. And so again, the solution is you can scale, but you have to have a strong vision and architecture to make it possible. Netflix is another good example. let me do some name dropping here because I have an interesting connection to Netflix that may not be so obvious. You may know of my work in the early days of visual modeling and my work at Rational. So we built up the UML. We built this thing called Rational Rows. All of a sudden, Rational was making lots of money. Yay, money. And we started on this round of acquiring companies. And we tried to buy companies that were sort of filling out the software development lifecycle. One of them was a company we bought by this requirements company out of Boulder. Ed Jordan met with me and said, hey, you need to talk to these guys. So we did. It was a company led by Dean Leffingwell. His name will come back in a moment. Another one was we bought this company called Pure Atria out of Boston. Pure was a company that was dealing with garbage management tools for C++. C++ was just emerging at the time. Atria was a company that had built out a configuration management tool. And great guys, they hired this gentleman by the name of Reed Hastings as their CEO. And so the company formed. We bought Reed's company. Reed, you may know, was the founder of Netflix. And as the story goes, Reed stayed with us for about a week or so. He realized, oh, I'm a terrible CEO. And so he took the cash from our buyout, and it's a lot of that cash he used to form Netflix. Netflix has gone through, by their count, 4 or 5 major architectural transformations. And they too, at the core, are a largely agile team. But again, it's a strong architectural foundation that made it so. Facebook's the opposite. Now, what I'm about to tell you is my personal experience. It's not that of any other buddy living or dead. It's not reflection of my employer. It's what I see. So if you work for Facebook and you're offended by this, hey, sorry, but I'm just telling you what I found. I had the opportunity to work with Facebook in their earliest days. When they were small enough that all of their development staff could literally fit within one room. And I had a long discussion with them about architecture, which they seemed to not care about, didn't resonate with it at all. And as I was leaving, I was asking them, tell me about your architecture and how you organize your teams. And the development manager, it wasn't Zuck, he'd hired a guy at the time. And he said, oh, yeah, see that woman over there, she's responsible for messaging. And that guy over there, he's responsible for the news feed. And this person over there, they're responsible for all the picture sharing and such. Well, that's interesting. And so in effect, they had agile teams of one, and they scaled what they were doing by having everybody in the same room. And so you could get this flow of information. My parting comment to them as I was leaving was, this is interesting, but it's going to fall apart the moment you guys don't fit within the same room. And indeed, it's proven to be so. For better or worse, if you look at Facebook on the outside, they have, I will politely say, less than optimal user experiences. They have less than optimal, I'll be outright and say it, ethics with regards to the management of user data. And so that's reflected in their architecture. Kent, by the way, was hired on later to Facebook, and he tried to help them to get more agile approaches. Talk to Kent, you ought to have him talk about his experience, but let's just say that he eventually left Facebook because I think he found it very difficult to change their culture. Very, very different culture inside Facebook. Citibank is a great example of an example of trying to use agile at scale, because much like Netflix and much like every financial business or telco, what you'll find happening is they've grown by acquisition. So you might like to have organically all these agile teams growing up, and that's wonderful. But the problem is, how do you scale it to the level of a multinational bank? And the way that Citi did it is they said, yes, we're going to have these individual agile teams and we'll grow them, and some are good, some are not so good. We'll try to infuse the self-organization of teams. But we're in the business of making money for our customers, our shareholders. We have to have some control. And so they evolved the notion of, in effect, an architecture board that drives it. So step back for a moment. Notice the common theme that I've said here among all these war stories. That what you're seeing is that, yes, agile works, but it doesn't work in isolation. teams of agile teams don't necessarily well self-organize. And so the principles of agile may not necessarily scale to a multinational kind of organization, but it really does require some discipline on the top, and that's okay. So now let's look at it from a different point of view. If you look at your classic web-centric system, you're going to see a lot of pictures like this. Now I've got a whole nother lecture about architecture, and I'm trying to write a book about it, in fact. But you'll see, dozens of these diagrams in your engagements. And I dare say, if you're involved in web-centric systems, this is your part and parcel of what you do. By the way, it's deliciously ironic for me to realize that folks like Amazon are rediscovering the value of visual modeling. It's like, well, yeah. And by the way, these kinds of diagrams are sort of a combination of what we would call deployment and component diagrams. They're sort of a mixture of the two, and they're great. But if you look at it from a microservices perspective, you get something that looks like this. That some brave soul took the microservices from Amazon and Netflix and did a study of how they're interconnected to one another. And thus we have reborn, you talked about big balls of mud among monoliths. These are big balls of microservices that emerge. And it's only through the clustering of these around a context, which is, by the way, why I love domain-driven development, because it helps us provide some order to this chaos that gives us some kind of control. It prevents these from degenerating into big balls of mud. However, as I said, there's more to the world of software-intensive systems than web-centric platforms at scale. So I would imagine, and I don't know, where most of you men and women come from, but I dare say most of you are probably working in this former world. But there's another world. For example, let's take a look at the world of apps such as Facebook. Go to the Computer History Museum again, and you will find the entire source code for Mac Paint. I had the wonderful opportunity to do an oral history of the two inventors of Mac Paint, and they provided the source code to the museum. You can look at it. It's written in Object Pascal. It is one of the most beautiful pieces of software I've ever seen. It's small, it's understandable. Now, let's move to Photoshop, though. Different beasts altogether. Turns out, architecturally, they're very, very similar. So I had a chance to meet with the architects of Photoshop. There are two of them. As the story goes, one of the two brothers that started it, he was working at Industrial Light and Magic in special effects for Star Wars. And they built this really cool system to do some of the fight sequences. Their boss, the gentleman who took over CEO of a company called Digital Domain, the company that John Cameron used for all the special effects in the Titanic, which is another story. He went to Lucas and said, "Wow, these guys have built some really cool software. George, what should we do with it?" And George said, it's just software, let them have it. And so that's how those two brothers got the rights to the code that became Photoshop, which they then ported to the Mac, which then, well, the rest is history. And it is the dominant image processing software for graphic artists everywhere. I had the wonderful time of sitting down with them and said, "Tell me your architecture." So as it turns out, there are two major code branches to Photoshop. And at least this was a few years ago. One for the Windows platform, one for the Mac platform, because they were really fundamentally different at the bottom. So I had them draw a picture. This is a common thing one does in child and family therapy. You have a dysfunctional family, you go to a child and say, "Draw me a picture of your family," and they'll learn something. It was fascinating because for about an hour, these two would sort of argue back and forth over the table. They finally came up with a description of it. As it turns out, the Photoshop architecture, Photoshop's about 15 million lines of code these days, was very, very simple. It had maybe a couple of dozen important classes, all built around this idea of a tile, which scales. It had a few dozen design patterns, and everything flowed from it. So in order to contribute to building out Photoshop, if you were brought into the team, its architecture was very, very understandable. So again, architecture rules in these cases. Well, this one's very different. Let me give you a bit of a history again. This is the control room of the SAGE, the semi-automatic ground environment, which evolved at the height of the Cold War in the United States in the 50s and 60s. In fact, it was operational until I think the early 70s, if I'm not mistaken. Look in the background, you'll see these consoles with the circles in them. Those were an offshoot of the Whirlwind computer from MIT, and they are the predecessor of what we use even today in air traffic control centers. So this was a system that was designed to collect real-time radar information from across the United States and Canada in a system called the BEAMUS, the Ballistic Early Warning System, and its predecessor, the DEW line, the Distant Early Warning System, worrying about Russian, Soviet bombers coming across the Arctic. And that would be all fed into these places and provide a real-time statement of what was going on in the attack vector. At its peak, this was the largest software project that anyone in the world had attempted, and took about, by their records, 30-ish% of the entire programming skill set of the entire United States. It was huge. It was during this time frame that we were at the cusp of the programming priesthood, if you will, because it was recognized that traditional waterfall methods simply weren't working. But as it turns out, that the architectures developed here are an awful lot like the architectures here. This is the Aegis system. It is it's basically, how would I best describe it? It's a system that has a particular kind of radar, phase array radar, non-moving radar that detects incoming threats and directs weapons to it. And it has an architecture that is not unlike the SAGE architecture. And as it turns out, it's a very similar architecture you see with any air traffic control system in the world. I had the chance to work on both the US and Canadian air traffic control systems. In the US, this was, here we are back in the 90s or thereabouts, when the US, the FAA Advanced Automation System was in full swing, recognizing with the growth of air traffic, the US had to replace its air traffic control systems, didn't handle the capacity, because then we were dealing with just simple radars and these handwritten notes that people would do. So thus was born this. And I worked with Hughes, IBM. I was not at IBM at the time. IBM bid against them. IBM won. And I remember after the bid was won, going in and did the IBM project, again, before I joined IBM. And the IBM program manager was very proud and said, wow, we were excited we won this multi-billion-dollar contract. We have built these two buildings. This building over here is where we're putting our requirements people. This building over here is where we put our developers. And of course, my reaction was, oh my God, you are so screwed. Because they had built a structure that made it impossible for their teams to organize and deliver in a rapid way. And as history will show, the FAA Advanced Automation System had some challenges. Canada was a completely different process. It was, both of these, by the way, were written in Ada, and they used Rational's tools to do it. And I worked with Hughes, and their architecture was then carried over and led by a gentleman by the name of Philippe Kruchten. Philippe, a wonderful, wonderful guy. He became the architect for CATS. And there were so many things that I've learned from him along the way. One of which is his notion, go read the paper, the 4+1 model view. But again, what you had here is they were successful because they had a strong architectural vision by a guy. By the way, Hughes was so successful, they took that same design and replicated it through most every air traffic control center within Europe. So if you're ever flying again, you're flying upon code that has its origins in Ada, that has its origins in SAGE, that is all very well architected. So you can thank that. There's another example, and this is kind of a counterexample of complexity at scale. And it's, of course, the Boeing 737 MAX, in which you had, indeed, agile teams building out the various avionics parts of it. But why were there crashes? because there was a single point of failure in the systemic design, one little pitot tube that sent information that was important relative to the autopilot. And if that sensor was in some way impaired, in which it was, then you'd get erroneous data, which would cause the system to do weird things. In this case, people died. So what's the lesson here? Agile works, but you still must take a systems level perspective, because just bashing things together and expecting them to have system proper behavior doesn't necessarily happen. So let's go back to the first principles, because this lecture is about how do you scale Agile? Well, it begs the question, what dimensions in which are we talking about scale? Well, one of which is number of simultaneous users. I've got 1 million users. Well, we know how to do that these days. Couldn't have said yes a decade ago, but we kind of know how to do it. And this is why things like Kubernetes has arisen. This is why Elastic Cloud has arisen. We know a number of patterns. And what a lot of Agile teams struggle with is basically, we know the patterns, how do I apply them? This, by the way, is why I think Kent and Ward were so successful in the earliest days, because these two guys are brilliant programmers, and they carried in their heads lots and lots of patterns that they knew how to apply. So another way of scale is the number of concurrent transactions and activities. It's like, well, this is the Bitcoin problem. Bitcoin's mechanisms can handle, a few, maybe 1,000 transactions per second if we're lucky. You see the Lightning networks, which tend to do batching, which try to improve it, but you're not going to get to the scale of what Visa has done, where we're talking potentially at peak 70,000 transactions per second. But that being said, we know how to do this in theory. We know the clear architectural patterns, how to do this. So there's no novelty in that sense. Then there's the issue of volume of data. This is also a problem of scale. It's like CERN, for example, dealing with when one experiment, I may generate a petabyte of data in just one experiment. We know how to do that too, in theory. We have clear architectural patterns to do so. So in each of these cases, Agile works easier because those patterns exist and we can fall upon them, and our teams can properly organize our skill sets to amplify those patterns. But now it gets harder. If I'm building a brand new system that no one's ever done, there are no patterns to do it. So I've just got to try stuff. And that's where the notion of continuous integration plays a role. This is where Agile teams can shine, but I have to be careful about the economics of it. If I'm building, something that goes boom, and I say, well, let's try it, and oh gosh, this thing just killed 1 million people, let's try it again. You can't do that. And so novelty may be fine, but there are also costs associated with it. There's issues of complexity and scale, that I may build a simple thing like, the next generation Tinder or Grinder. We sort of know what the behaviors of those systems are, and we know where the edges of them are and the like. But if I'm building something that I've never done before, that has extreme complexity, like what we're seeing today in many AI systems, it's getting really hard. You can't reduce the complexity of a system. The best you can do is manage it. And then there's the issue of risk, that if all I'm doing is something that if I fail, then, I just go to another venture capitalist and get some more money, or I start a new business, that's disposable software. Cool. Hey, go for it. Do your Agile stuff. That's fine. It's wonderful. But all of a sudden, if my company depends upon it, if my country depends upon it, if civilization depends upon it, then you're going to stop and think, well, wait a minute, maybe failing early is not so good, because failing early might have devastating consequences. So that end, when you consider the problems of Agile at scale, you have to ask yourself which scale, and find out where the sweet spot is for you within it. To call ourselves software engineers is a funny term, because we're really not engineers. It's like, calling social science a science. It's not like people have lots of testable theories in that cases. I still like to call it an engineering discipline in the sense that it is the problem of trying to build solutions to problems for which there are dynamic and static forces upon us. And we try to build systems that resolve those forces in meaningful ways. So you got the classic ones: mission, cost, schedule, complexity, ceremony, et cetera, yada, yada, all the ilities, maintainability, portability, et cetera, and increasingly the costs of legal and ethical issues. This is where engineering is all about. So if you are a team in which these risks, these forces are well understood, then Agile is easy and it scales. But if these risks, these forces are great and volatile, then it becomes much more difficult indeed. In fact, Dave Cheney came up with this chart. Here's a great way to describe it. Architecture is an invisible feature, visible thing of positive value. Bugs are visible things of negative value. And technical debt are the invisible things of negative value. You want the positive stuff, obviously. And so what can you do in your methods to drive us there? Now, you'll notice the theme I've said thus far is that the one thing I found consistent among applying Agile at scale is the presence of a consistent architectural vision. So what's architecture? All architecture is design, not all design is architecture. This by the way, is another hour-and-a-half lecture, so I'll be quick about it. Architecture represents significant design decisions, where significant is measured by cost of scale. And in the vision, the beginning, architecture is a statement of vision, but in the end, you end up with an architecture that's a reflection of the billions upon billions of small and large decisions that are made along the way. Some architectures are intentional, some are accidental, most of them are emergent. And that's why Agile thinking fits, because Agile approaches allow us to have these things that emerge. So yes, the code is the truth, but it's not the whole truth. And this is where I get into some, violent intellectual battles with diehard Agilists, because they say, oh, I don't need no stinking architecture. Well, it's like, yes, you do. Imagine if I'm writing code that has to be maintained and your children's children are going to be reviewing this code. Where does the truth lie? Because there are things that are done in the design process where there's a loss of information from the implementation, from the vision to the implementation. And those are the kind of things that I want to capture in things beyond the code itself. Excuse me. So here's another way to look at it. If you put on the left-hand side, this is what I imagine I want to build. On the right-hand side, this is the running implementation. These are the things that are between imagination and implementation. The domain of physics and algorithms are the problems of computer science. From algorithms on up to the human issues are the domains of software engineering. And it is largely that latter part is where we worry about applying our Agile teams. I'll skip over this one. So design decisions encourage what a stakeholder can do, but they also constrain what a stakeholder can't. And so it's important to keep architecture as an artifact because it allows me to preserve my tribal memory. It gives me something I can reason about beyond the code itself. And it allows me to be a mechanism in which I can intentionally attack risk. Now, I am all for architecture diagrams, but I am also all for one in which I throw most of them away. And I'll only keep those kinds of visualizations that capture things that are not evident in the code itself. A good architecture is characterized by crisp abstractions, a good separation of concerns, clear distribution of responsibilities, and simplicity. Everything else is details. And furthermore, all such systems are full of patterns. Focusing upon those patterns and cross-cutting concerns will yield a better architecture. And this is why I said that Kent and Ward were so successful, because they have a lot of architecture patterns in their head. And this is why you see many cloud-centric systems to be amenable to Agile systems, because we understand these kinds of patterns already. In fact, we've codified these. Go read Mary Shaw and David Garland's book, Software Architecture, that started it all. And there are a few dozen common architectural patterns that we know about. And that's a good thing. But here's the issue. In mature domains, a lot of architectural decisions end up being made in frameworks. Someone will say, hey, let's go use Keras. Let's go use, Kafka. Let's go use Kubernetes. Let's go use TensorFlow. By making that decision, which may be an informed decision or one that's simply because you used it before, you have made a major part of your architectural decisions. And therefore, you've begun to constrain what's next. And that gives you the context in which you can build out your teams. That's great. But in novel, complex domains, you can't do that. And really, this is where this notion of evolving from failures to successes becomes important. Here's a way to think of it. If you're building a system for which there's no risk, it's like a doghouse. You build a doghouse, you don't need blueprints. You just go find yourself a pile of lumber, you build it. If you fail, then you build a new doghouse. If you really fail, you just get yourself a new dog and start over again. Sorry for all the dog lovers. On the other hand, if your money is involved and you say, well, I'm not just going to hand over $1 million to my contractor and say, hey, see you in a year. You're going to say, I want to talk about what I want. So you actually do blueprints, you do an architecture, and you test it along the way. This is where, this is why we have building permits and building inspections. And so it becomes a little bit more ceremony. When you're starting to move to the notion of a high rise, and you're now dealing with potentially $1 billion, then my goodness, you really do want to spend more attention with it. But you have to be careful because even in those circumstances, unexpected consequences can arrive. Think back to your physics 101. What happens if you take a concave surface and shine a light that is at infinite distance onto it? You get those light rays that focus at a point. Well, imagine building a wonderful, wonderful high rise. It's beautiful, it's wonderful. It has a concave surface that has mirrored surfaces on it. And oh, by the way, on certain sunny days and times of the year, it becomes a death ray that burns cars below. So yeah, you end up with architectural things you may not have seen before. Here we go. I'm gonna skip that one. Sorry, it didn't come well with the animation. A lot of the problems that we face today are not the building of doghouses, not the building of houses or skyscrapers. They're problems of city renovation. Paris, I love this city, my favorite city in the world, beautiful, beautiful place. But imagine if you were Elon Musk and said, hey, I want to put a hyperloop through the center of Paris. People would say, I don't know how to do profanity in France. So French, you'll have to help me out here. But they'd probably say some things that I could not repeat because it'd say, no, I don't think so. Because now you're dealing with changing legacy systems. And all of a sudden, your degrees of freedom are very, very much changed. Hang on, let me shut these up. Another spam phone call, sorry. And so this is where a lot of projects are. Yes, you can carve off pieces of it. I want to renovate this building, but if you want to make system level changes, it becomes much more difficult. But what we have found that even in the presence of scale, the principles I talked about at the very beginning, they still hold. But as I said, agile methods have become a bit of a cargo cult. So bear with me for a moment. Oh, okay, sorry, I wanted to learn some French profanity. So Christina, you'll have to help me after we're done here. So here's a way to think of it. And this is, remember I said scale is a multidimensional issue. In this case, the y-axis coming toward you, that's complexity. Here, the y-axis is going up, that's risk. The z-axis coming toward you is complexity. The x-axis I've just put as ceremony. What you find happening is that, and this is true as most methodologies, as risk and complexity rises, there is this tendency to increase ceremony. Because it's like, oh, but we want to document what we do here. And so here are the corner cases. Let's apply all this. Let us now turn to 5 ways in which people have tried to scale methods. And I'm not condemning any of them. I'm just telling you this is what exists in the world itself. I'm not recommending nor condemning any of them. One of these is SAFE. Now, it comes from a name you may have heard before, Dean Leffingwell's company. SAFE is the Scaled Agile Framework. And This is a methodology that I would say is relatively high ceremony when it comes to scale. There's tremendous methodology around it, and it really was intended for systems of tremendously high risk. So you first may look at it and say, I have tremendous tissue rejection. But with all due respect to both you and them, keep in mind that you may be building systems that are not of the scale of risk, the kind of systems for which SAFE is necessarily targeted. This is targeted at systems that have organizational-wide, multinational business-wide, as well as nationwide, civilization-wide projects. And so it makes sense that ceremony increases, but I'm not certain that necessarily scales down very well. The next approach that people have tried in this place is that of the Scrum of Scrums, coming out of Jeff Sutherland himself. And what's intriguing about this, it's an attempt to scale Scrums simply by applying, in effect, a bit of recursion, that we see Scrum teams doing what they're doing, and then I have those group organize and do other groups, which, by the way, apply the same kinds of techniques as the groups below them. This sometimes works. It sometimes works if and only if I can easily decompose my systems into such groups. But if I have cross-cutting concerns, if I have problems of systemic architecture, it doesn't necessarily apply. At least in my experience, it hasn't necessarily scaled to that extent. So it works in some cases, but not all cases. The good folks at Spotify have taken an approach that they recognize the presence of cross-cutting concerns. And that's better. It, in a way, attacks the problems that Jeff's approaches doesn't necessarily do so. And in effect, it says we're going to take the organization and adapt the business to the organization as opposed to the reverse. And again, that's fine. Spotify has a particular business model, and it's possible for them to do so. So what you see inside Spotify is an Agile at scale that works for them, but remember, they have control over their business in a big, big way. So again, your mileage will not necessarily, will vary because you are not a Spotify necessarily. Then we have the notion of disciplined Agile, which I'm going to tell you honestly, Scott, love you dearly. I'm not sure I understand it exactly, but it in many ways is an attempt to take the best parts of a lot of different things, XP, Agile modeling, et cetera, et cetera. And so I think it's right in the sense that it's attempting to get the best of it, but I have not seen it necessarily applied to systems of the scale in which I was speaking of before. What you tend to have happening in the worst is people will take things that reflect their own biases as opposed to stepping back and necessarily doing the right thing. And then there's the large scale Scrum, which I've not seen in the wild. It has sort of the same kinds of issues that I see with Scott's approaches. It's an attempt, and a very good one, to try to bring together good ideas. And I've seen it applied in those places that are classic web-centric things for which we know organizational patterns and know design patterns. So again, it may apply to you if you are in those domains, but it doesn't necessarily do so if I'm dealing with novel high-risk things. So this causes me to fall back to design principles, basic principles. And I always go back to Dave Parnas's paper, A Rational Design Process, Why and How to Fake It. Because this is the essence. No matter what process you use, no matter what you call it, my experience has been that every healthy project looks like this. I often get parachuted into projects and they say, Grady, help us out here. And, help me, Mr. Wizard. The very first question I will ask when I go into a project is, tell me about your rhythm of releases, independent of their methodologies. And if they tell me, oh, we do CI/CD, and I'll go deeper to make sure that's really the truth. If they, on the other hand, say, we don't really have a pipeline, we sort of integrate when we can, or we do integration on an irregular basis, fix that first. Because unless you fix a CI/CD pipeline, then it's impossible to have any kinds of organization around it. And it's that kind of heartbeat you want. But be careful, because you can have too rapid of a heartbeat. I spent time with the Microsoft Word team, and they proudly told me, yes, we do a build every night, and we then have a set of regression tests against it, so our people can come in the morning and and build upon it. But then I observed that's great, but the downside of such a process is that your heartbeat is so fast, you have no way, no incentivization to make your system simpler. You're always pushing new and new features. So be careful of a CI/CD pipeline that doesn't give you time for your heartbeat to rest and allow yourself to refactor. When eBay was, I think, really at its peak, when they were doing great things organizationally and development-wise, they spent 10% of their development budget on refactoring. I don't think they do that anymore. But it's a representation that even in the presence of large systems, even in the presence of Agile, if you focus upon continually improving your architecture, continually eating away at that technical debt at a system level, that's a good thing. So let's explain the lines. And by the way, this was written on the back of a napkin by a dear colleague of mine, Bran Selleck, and really in some early days of methodologies. The red line indicates a period of discovery, that every project has this. At the very beginning, you're saying, what the heck am I doing? And you continue that through the project. Then you have a period of invention in which you say, hey, let's try this, let's try that. That's the white line. Then you have a period of implementation, that's the green. Every healthy project looks like this. And the important thing is there is an overlapping of those three. At any one moment, you are inventing, you are discovering, you are implementing in varying degrees. Every project does that. Every successful project does that along the way. So a solution to any problem is really one of an incremental and iterative process with these periods of punctuated equilibrium. Quick aside, I am using a phrase here from the book, The Sciences of the Artificial by Herbert Simon, the tremendous gentleman, an economics guy and also an AI guy. And what he pointed out is that he looked at all complex systems, be it human systems, be it organic systems, be it social systems. They had these periods of stability, what he called punctuated equilibrium. By the way, evolution works along the way too. So in effect, we can step back and say, hey, if I'm building these things, you do the hard part first. And if it works, it's easy, it's great. I'm an engineer. If it works, then hey, all power for you. All design will contain an irreducible kernel of problems. And if I know what those problems are, then hey, I'll just apply them. That's where Kent and Ward shined. That's where your agile teams that work magically work well, because you've got a set of people that know those patterns. But if you don't know those patterns, you've got to just try stuff along the way. Development, therefore, takes place at two levels, architectural and implementation, and they both happen simultaneously, and they both act with each other as well. So your process, when you move to scale, looks like this. It really is agile on the outside, and I'm going to use a dirty word here, kind of looks like waterfall on the outside. This is the very point that Parnas is making, that you fake it, that it's really not waterfall, but it's really, you're looking at it from those levels of overlapping discovery, invention, implementation, and you sort of arbitrarily say, this is requirements, this is design, this is implementation, but you know that those are all fuzzy. But along the way, you're doing CI/CD, and most importantly, you're always driving it by stories, and you're always testing those along the way. So that means in the small, I'm doing it with a set of user stories. I have my customer on site. It's a simple design, yada, yada. That's great. But oftentimes I can't put all million of my customers there. So here's what I have to do. I'm going to use my working software as how I measure my progress. Churn is another anti-measure. When I see myself looking at the same bit of code and I keep committing and changing it all the time, that indicates I've got some problems there and I'm going to put some energy upon it. Yes, I want to collectively have everyone see my code, and this is a problem that some organizations have a real problem with because there are such empires built around code. But believe me, it is a very liberating thing. And along the way, you have to begin to codify the design patterns you've built. This is why I speak of refactoring to frameworks that may be brought in externally or frameworks you create yourself. That's exactly what Amazon did. There were no such frameworks, so they built their own, and that's where AWS came from. All good design patterns eventually mature themselves into those kind of frameworks. Agility at scale with quality requires CI/CD with measurable executable, delivered by teams with local responsibility, engineered in the context of a global architecture. Every one of the cargo cults things you talk about, they're this, but they're applying lots of ceremony upon them. So depending upon your risk, go for it if you want more ceremony. But the heart of scale is this. Architecture is important, and it's the way you'll get agile teams working together. Now let's talk about organization. Show me your organization, and I'll show you the architecture of your system. Some groups are small teams, they're banging pots together, and occasionally you'll make great music. Really good agile teams, they're like a jazz band. It's magical to work within them. You've got a Chick Corea, you've got a Miles Davis. Man, you live for the day in which we're within those kind of systems. Most of us, we're in orchestras. We're not the conductor. We're part of the band, if you will. And so some degree of ceremony is not just inevitable, frankly, it's desirable, and that's okay. Meaningful architecture is a vibrant process. All vibrant architectures either evolve or die. And indeed, old software never dies, you have to kill it. So what do you do when you have old software? You can give it away, you can ignore it, you can put it on life support, you can rewrite it, harvest it. Again, your mileage varies. Depends upon the economics of your situation. In some cases, you do want to kill it. In other cases, if your business depends upon it, you got to keep the lights on. So you're going to keep refactoring it along the way. All right, let's shift for a moment because I want to make sure we have time for questions. And by the way, thank you all for sticking with me. We've got a good solid group of 30 some. So you've either fallen asleep at your keyboards or this is useful to you. So either way, thank you for hanging here. We're going to make a pivot for a moment. And we're going to talk about something that's in a very different world. Most of you, I would imagine, are working in the world of symbolic computing. This world is about calculating stuff, manipulating decision-making, cool, large volumes of data. It's about model making and model using. But there's a different world. I'm working mostly in the world of AI these days. I've made the transition myself. And that's why you see all the robots around me. And I'll bring up the thing in a moment. Most contemporary AI is about pattern matching of signals on the edge. If I'm doing facial recognition, or hey, it's a cat, or hey, there's a painting defect, or hey, it's a stoplight versus the moon. Yes, Elon, I'm pointing to you in your FSD, full scale, the full system driving, full self-contained driving. It's really about pattern matching on the edge. And it's a large matter of inductive reasoning. We haven't yet gotten there in the AI world about decision-making, about abductive reasoning, about causal reasoning, about common sense reasoning. If you want to learn more about causal reading, go read the Book of Why by Judea Pearl. If you want to read about abductive reasoning stuff, gosh, where to begin? Well, Judea also has some important things to say here. Abductive reasoning is that of model building. There's a great paper by Rodney Brooks called Intelligence Without Representation, very influential upon my way of thinking. Go read the works of Gary Marcus along the way as well too, and you'll see some things in this space. We aren't there yet, but a lot of the things you see happening with AlphaFold, AlphaX, its various incarnations, the work of OpenAI, of GPT-3, it's more of the former than it is the latter. So little history here of how things have evolved. The idea, of course, is we're dealing with a completely different computational platform, one based upon not not symbolic approaches, but neural approaches, which, by the way, both neural and symbolic approaches are Turing complete, Turing equivalent, absolutely the same. Thing is that it's kind of bio-inspired, that, you know, our brains have about 100 billion neurons. If you happen to be a certain ex-president from the last 4 years, it might be a smaller number. That's another discussion unto itself. Human brains run around 20 watts. GPT-3 training, AlphaFold training took terawatts to actually do them. So we know we've got some work to do. And here's the thing, the typical neural network, the neuron that we model here, is a small fraction of what human neurons do. So if you go back to the very beginning, you see Newell and Simon. It's the same guy, Simon, I talked about before, working in the area of symbolic computation. The idea that logical approaches would lead us to cognitive systems. And so it led to a whole series of machines. And much like early symbolic computation, the machines evolved with the architectures themselves. You saw the beginnings of stuff like this. This was the very first artificial neuron. It's a thing called the SNARK, built out of MIT. It took, 5 or 6 vacuum tubes to make one neuron. Now we can certainly shrink them down. And it led to the rise of things like Lisp machines, where people said, we're going to model everything in Lisp because that's the way we do brains, and we build machines to supplement them. This is also what led to the connection machine, which was an attempt to do sort of multi-agent architectures along the way. And then it led to things like Watson Jeopardy. Watson Jeopardy is sort of the second generation AI kind of systems. It wasn't symbolic in nature. Actually, I call it more of the third generation. It was more statistical in nature. And yeah, we threw hardware at it. We threw lots and lots of computational power to make it work. The good folks at OpenAI and DeepMind have done the same. That both Alpha X, its various incarnations, and GPT 1, 2, 3, and beyond, all throw lots and lots of hardware at them. Now, NVIDIA, bless their soul, is pivoting to an interesting direction because they're trying to take this same kind of stuff and move it toward the edge. So here's my observation. Lots of cool stuff happening on the edge here, where we see more and more novel kind of architectures possible because we're moving away from the cloud to the edge. The pendulum is swinging. Google, of course, has their TPUs. We at IBM have taken the approach of a project we call North Star, which is taking artificial neural neurons and actually shrinking them down to silicon itself. In fact, we've gotten to the point where the team did one demonstration. We packed as many artificial neurons into the same space as the human brain, as the human neuron has. Problem is, it didn't have the same number of synaptic connections, yada, yada. So there's ways to go. So I spoke of the generations. We've seen several. The earliest days were, the earliest days of neural networks, the connectionist approaches. Then we saw symbolic approaches, which you can break apart to the ideas of Newell and Simon, and then later on the ideas of Feigenbaum. Now we're in the statistical approaches like you see with Watson, and even more so today, we're in the deep learning phases. Here's the really cool things that's happened. The AI community has been rediscovering the common patterns of development that we've come to love in software engineering. And so GPT-3 is based upon the transformer architecture. AlphaFold also uses the transformer architecture, plus some interesting tricks on it. But it's a pattern, and they've begun to recognize those kinds of patterns. So really, really cool stuff along the way. We've also begun to realize that there are common approaches in process as well. If you go to your average organization, multinational organization, they probably have several hundred AI projects taking place. Most of them are small. Most of them are model building one-off things, saying, I've got this chunk of data, go try something about this. And they go off and build them. But what we're discovering, and Andrew, one of the leaders in the AI space, observed exactly this. When you move to production, it's just like code. Neurons are a code base. Models are a code base. So here's the good news. the AI community is discovering that. And the other good news is that it fits within Agile approaches and even at Agile issues of scale. So for most of us, the problem is we're not going to go off and build the next AlphaFold. Not everyone has the privilege of doing so. Most of us are going to take AI components and begin to inject them within our larger systems. And the good news is we see a path to do so. So again, every approach here is computationally equivalent, but they have different advantages and efficiencies. Each has different scale, latency, resiliency, et cetera. So the problem we are on the cusp of is dealing with the integration of symbolic and neural systems. Now, if you want to go way out, it's now quantum systems. So we're probably a generation or two away from this truly entering the mainstream. Quantum computing is architecturally, we're many years behind where the AI world is, but they too are beginning to discover design patterns. In fact, recently you'll see this announcement of IBM and CERN, because there was a discovery by a team of researchers in Japan of a quantum kernel algorithm, which allows us to do some really exciting things, even with a small number of qubits. I don't know how to organize a quantum development team. We're just trying stuff. I don't know how to build a quantum architecture because no one's built one yet, but it's going to come. And experience tells us that it's going to follow the same path we've seen in symbolic systems as neural systems and here as well. In fact, let me step back for a moment and we'll look at the grand set of things. We'll have time for some questions here. If you look at the entire history of computing, this is sort of where we have been and a focus upon the dominant problem at hand. The earliest systems we built were all mathematical in nature. A new ballistics table, a new nuclear simulation. And so we were just dealing with the fundamentals. And then as I started dealing with classic business problems, lots of data, then managing complexity became the issue. As it became more personal, then HCI issues played a role. And then as I moved to the web, scale became an issue. So here's the cool thing. Every one of those four, we kind of understand patterns in how to do those, both organizationally and architecturally. That's great. That's a sign of the ways our discipline has emerged. But we're going to the next stage. We're dealing with systems in which we build imagined realities. And I'm not just talking about virtual reality and augmented reality. I'm talking about video gaming, in which you immerse yourself in the world. I'm talking about augmentation of the human body through various ways. I'm talking about projecting ourselves into an entire atmosphere of computing devices. The diagram from Copenhagen I showed you earlier. These are the realities we can only begin to imagine. And as a gentleman said back in the 50s, I think it was, we're living in an enchanted world, a world of our own making. And now issues of ethical and moral problems dominate for us. So this is exciting stuff. So lesson here. Can you scale Agile to large multinational systems of human importance? Yes, you can. And how does one do it? The same way we built systems of scale throughout civilization's history, we apply the fundamentals to us. Let me leave you with this. It's a sort of an inspirational thing I like to leave in all my lectures, and think of it this way. Software is the invisible writing that whispers the stories of possibility to our hardware. Software is the invisible writing, and it whispers the stories of possibility to our hardware, and you are the storytellers. So go off and write some great stories. Again, I am infinitely accessible. Feel free to reach out to me. And I think operators are standing by. We can have some time for questions.
Yes.
So, Christina, Kenny, I'll turn it back to you guys.
Perfect.
The first reaction is this one.
Yeah.
I never ever had this feeling to need to clap for somebody. It was, I think most of us are speechless.
Yeah, I see a lot of reactions also on Twitter. A lot of questions already answered, so thank you for that. I'm gonna put down everyone's allowed to unmute themselves. So if you have a question, unmute yourself. And we also have some questions on the chat, right? So let's start with one. How do you work with the organization which seeks for quick wins in trendy buzzwords, but lack of patience to grow the product's team capabilities?
That is a great question. There are two things you can do, three things you can do. The first is leave that organization. If you find it's futile, then just say, screw it. I'm not going to waste my life on it, because there are lots of places you can contribute. That is a viable decision one can make. This is why I say every line of code represents an ethical and moral decision. And a decision to work in one place is such a decision. So you can leave, go for it. Now, you may not have the opportunity to leave for economic reasons or emotional reasons or whatever, that's fine. And so you now have one of other two choices. The next choice is suffer in silence, which you say, well, this really sucks, but I'm going to keep doing it. The third approach you can take, which I myself try to do, is to try to be an agent of change. And you do your best. You try to keep nudging things along the way. You may or may not have levers within the company to do so, but at least at the end of the day, you're going to be able to go to sleep and say, I have developed with my own sense of integrity and vision, and I am living my life consistently with that. If you can end your day doing that, then that's a good day.
Thank you. I hope your answer or your question is answered. If so, let us know. Yes, I see so. So anyone in Zoom who wants to ask a question live?
But what about ones in Miro?
Yeah, I see Augusto raising, and then we can go on with Miro, Christina.
Yeah, great. Mm-hmm.
Thank you very much for the very inspiring talk. I was wondering if you could say a bit about how you made the transition from being a standard developer to an AI developer.
Great question. So here's the story behind it. My domain, my area of expertise is software architecture. That's just what I do. And I was acquired by IBM in 2003. So I was chief scientist for Rational from its foundation in '82. We were acquired in 2003. IBM and Microsoft were both bidding for us, and IBM won. I'll do another name dropping story. 2003, about a month later, I got a call. It said, hey, Grady, it's Bill. Hey, Bill, come see me up in Seattle. So I go visited Bill, and he sat me down in his office and said, it's not public yet, but I'm going to be leaving my role as CEO of Microsoft. And, I'm also Microsoft's chief architect. I'd like you to take that role. And I said, well, that's really cool, Bill. So I spent time with his lieutenants for a couple of months. And at the end of it, and I came back to him and said, Bill, I'm just, deeply flattered. This is, wow, what an opportunity. But, I've looked around the company, and Bill, you've got a really dysfunctional company. I'm not the person to fix this. So you need somebody else. So I said no to Bill, and I'm happy I did. So I continued on inside IBM, and I still think it's the right decision, because he needed somebody like a Jack Welch to knock heads. I'm a lover, not a fighter, so it was the right decision. So I continued on inside IBM for several years. Eventually switched over from the product groups to research, where I was primarily doing research in tools for software development. And we had a group led by David Ferrucci that was trying this experiment. We had a long legacy of good work in natural language processing. Most of the stuff you see Nuance do, they licensed it from us in the earliest days. So we had some great teams there. So Ferrucci and crew were off on this mission that was inspired by a guy who was my boss at the time, saying, hey, let's go see if we can win at Jeopardy. So the Jeopardy team was established, and they worked for about 3 years or so. By the way, I've got another lecture on the architecture of Jeopardy, because what happened is Ferrucci called me in and said, would you take your software engineering expertise and document the architecture of Watson for us? Because we didn't do it. So I spent time with the team, interviewed them, looked at the code, looked at their documents, and I basically documented the as-built architecture using the UML, using 4+1 model view. I had some really interesting discoveries about how they worked as an Agile team. 30-some people worked together. It was a brilliant team that did that. And because of the work I did there, IBM then asked me to lead an internal study that helped inform the creation of what became the Watson Group. I didn't join the Watson Group, but I wanted to stay in research because I thought there were some interesting things happening architecturally in AI. So from around 2016 or so, I worked on applying my AI skills to architectural skills. So bear with me because I'll tell you one more story because it explains the robots you see around me. This is a pepper from Aldebaran. This is a now from Aldebaran, and I've got lots of other small ones around here. Our team down in Austin was working with Hilton Hotels at the time. And Hilton said, we would like to take Watson technology and make an automated concierge to put in our hotels. So we said, that's cool. Let's use an anthropomorphic device. We used the Now, and we built a system around it. So the team did so using Watson services and a set of tools called Choreographer, which was from Aldebaran itself. And they found that it didn't scale. And there was no sense of liveness associated with it. So they, knowing what my architectural work was, they called me and said, Grady, can you help us out here? So I spent time with the team. Ray Chansey was leading the team at the time. I love the guy dearly. And I worked with this team and proposed to them an architecture that might be useful to them. Another IBM fellow was in the midst of this as well too, who was the CTO of the Watson Group at the time. He now leads our Edge activities. And from that, we were very successful, and the good folks at the hotel loved it. We deployed it to a few of their things, their hotels. This was, by the way, pre-Alexa. So it was kind of cool and novel. But then from the success of that, we started getting all sorts of companies saying, hey, I don't know that. Yeah, sorry, hang on. Alexa just woke up. She thought I was flirting with her. Let me shut her off. She does that when I mention her name. Sorry, Alexa, we'll talk later. So we had a number of other companies coming to us, hey, this is cool. So we stepped back and said, well, we think we have something here. What would be a long-term research project for us that could drive our agenda? And we stepped back and said, oh, obviously it's the mission to Mars, because the mission to Mars has two interesting characteristics. The first of which is, because of speed of light issues, you can't rely upon mission control on the ground. You have to take it with you. This is the HAL scenario from 2001: A Space Odyssey, minus the homicidal stories. That's not a feature. That's a bug. It's not a feature. So let's throw those out. Additionally, NASA wanted to put on the surface of Mars a set of robots before the humans arrived. Thus was born the idea of the Robonaut 2. In fact, as we talk here, I'll bring up a picture along the way to show you. So we basically took the architecture we had here and said, literally one afternoon, I said to the side, I think I know how to do this. And so devised a hybrid symbolic neural architecture that became a system we call Self that we applied to a bunch of places. So at its peak, I was leading a team of about 35 or so researchers across 6 laboratories, building systems that worked in that space. And so increasingly, I found myself, let me do a screen share real fast. Screen share, there you are, preview, just to be clear, that's me in the middle. The one on the left-hand side is a Robonaut 2. The person on the right is the inventor of the Robonaut 2. Cool stuff. We actually took the system that we designed and put it behind it to see if we could animate it. Very, very cool things. It led us to some work with an oil and gas company as well. So that's been my move to it. And increasingly, I work with our groups out of MIT on neural symbolic architectures. That's just what I do these days. And I'm intrigued by it because the things I know about architecture and symbolic systems, those lessons are repeating themselves. So that's my journey into AI. Oh, and I should throw this off here while I'm at it. Show you this thing. I got tired of using our external cloud, so I built my own cloud. This is a little cloud of 4 Jetson NVIDIA Nanos running Kubernetes, by the way, and it's what we've been running Self on. So yeah.
This is the future, Kenny. You saw it.
Yeah.
That's it. Learn it. I love Kubernetes. Kenny not.
I'm more a serverless person.
There you go.
Okay, I would have a question, if I may.
Sure.
You started this talk with about discussing about scales and numbers, and this project going 50 years or expecting 50 years of operations. How do you get and apply feedback for such projects? Well,
the good news is that the development process is going to last about 5 years, and there will be indeed tremendous progress, tremendous feedback. There are some things you simply can't test, but there are lots of things you can simulate. And once it's deployed, there are certain operational parameters that aren't necessarily going to change, and they will change relatively slowly. And those things that do change, there's a team in place to attend to them. The thing that's going to change the most, quite frankly, is the underlying computing framework, because I may specify a particular machine today. It's wonderful. It's the best of breed. 50 years from now, it's going to be nothing. So one of the challenges is you have to build an architecture in which you're relatively guaranteed that the compute construction you're using today is not what will exist in 50 years.
But can we say that at this scale, not this specific project, but at this scale, you cannot be really experimental and rely on feedback. You have to have a good plan, not only on architecture, but also halfway's waterfall or something, a proposal which you are quite sure.
Yes,
because
the first 5 years, the first 5 years will look relatively experimental, but once it crosses the threshold of confidence that it is correct, then it becomes relatively stable. Yes, there will be changes because policies change, UI changes, those kind of change. And so there'll be lots of changes at the edge, but not in the core. This is why, this is the same thing you see with the IRS. The core architecture of the Internal Revenue System is unchanging. This is also why I say that Amazon, Microsoft, Google, Facebook, Spotify, they are all legacy software companies. They are. Netflix has gone through 4 or 5 different architectural iterations. They're probably not going to go through another one. They're going to be a very different company if they are.
Thank you.
You bet.
So I see Rick raising his hands. So please.
Hi. I mean, that's probably a good time. Like, so kind of going back to the topic title, which is like 50 ways to scale your agile. My question is around this really around scaling up the system versus scaling down the problem, right? And that it kind of relate. There's 2 related things in there. Like, and I just wanted to get your take on that. So, because a lot of the these agile scaling, even with architecture, kind of like they're talking about scaling up the problem or scaling up the system. We do it this way at the team, and then scaling up that whole thing. But if you start looking at related scaling down the problem at the same time, right, and letting people take ownership of pieces of that problem, you can interleave and give people ownership of discovery and delivery, right? Discovery and delivery. And so kind of, I just really want to get your take on that.
Well, I think that's where Spotify shines, because they have intentional mechanisms that incentivize cross-cutting discovery. They move people around. They take the organizational boundaries of their teams so that they are intentionally outside of the silos. One of the common failure modes that I see in people trying to apply Agile at scale is that all of a sudden they built a whole bunch of Agile silos. And so they repeated the same problem again and again. Spotify fights it by having those organizational imperatives. So I think the short answer is, yeah, if you have an organization that incentivizes cross-cutting collaboration, that's the way you get the right mixture of things. Does it scale to projects of a multinational level? Don't know. And it's especially hard these days, given you can't travel, because I can't show up in one place. In fact, let me tell you a war story from Watson, because this is a good example of that very thing working. So Ferrucci pointed out at the very beginning, he was trying to solve this. He said, we've got a bunch of teams, one on the East Coast, one on the West Coast, that have the really coolest natural language understanding algorithms. This is awesome, but they don't work together. So he literally had one of the leads fly out from the East Coast to the West Coast and set them in a room and said, you two aren't leaving until you find a way that you can work together. And from that was born an architectural decision called UEMA. Architecturally, Jeopardy is basically a pipeline architecture, and UEMA is an open source mechanism to do just that. And so they basically said, we're going to solve it by coming up with a common architecture. Quick aside, I mentioned pipeline. That's exactly what AlphaFold does and GPT-3 do. They are both pipeline-like architectures. So we're seeing the AI world beginning to resonate around this particular notion. So go look up UEMA, U-I-M-A, and you'll learn all sorts of things about it. Incentivized cross-cutting collaboration is the aphorism to apply here.
Perfect. Thanks. So, Christina, do we have another Miro question?
It is one, but a big one. I don't know if we can, if you're still able to answer it. So why not? From Alexander, I think he is gone. As software engineering is all about solving problems, what modern software engineering should solve in the next 10 years? What are the missing parts of happy part in software development?
Great question. I'd answer the question in this way, that happily there are several centuries of systems engineering experience that we know works and doesn't. I think the biggest changes we're going to see in the coming decade are the problems of integrating AI components into symbolic systems. That's just a pragmatic issue. The last several years has been the problem of moving folks to the cloud. We still see that happening, which is an interesting problem, but it's not necessarily a problem that does anything for end users. Yeah, it helps in terms of global access and the like and scale, but doesn't fundamentally change the way in which I interact with systems. It's invisible to most people. But I think the introduction of AI components is going to be an important thing in the coming next 10 years. And we just don't know enough of how to do that I think this would be an exciting time. And of course, to follow that would be the quantum phase. I think the other factor here is, there are two other factors. The other factor is, as we see systems moving more and more into the interstitial spaces of society, as we see systems that impact individual human lives, then ethical and moral issues become more important. And I used to claim that every software development team needs a lawyer. Well, nowadays, every software development team needs somebody who reflects the ethical and moral issues of what you're doing. That even the simplest thing you do may have implications long beyond where you are. So that's one important change. The third one, I forgot. The short answer to his question is 42.
What
Thanks.
about IoT? You don't.
Oh yes, yeah, the IoT one. Yeah, the IoT one. Oh, okay. Yeah, yeah. Here's what's happening. So this is. Thank you. Thanks. You're a good reminder to me. So what's happening there is the pendulum I see starting to swing. That right now it looks like all the focus is on cloud, hybrid cloud, whatever. But now I see more and more stuff moving toward the edge. That if I get computational power on the edge that used to be in a mainframe, then all of a sudden it changes my architecture, that I can do things on the edge with my data that helps me relative to privacy and security, because I'm now not moving into the cloud. I'm guaranteeing it's sticking on my phone. That changes things, and we don't necessarily have the patterns to do that. So the pendulum's moving a little bit. There's a corollary to that, which is increasingly I'm seeing more and more people who are not trained in software engineering becoming software developers. And so what we call software engineering it's now quite a mixed melting pot, that you'll find within a given team, maybe a few people who have a degree in it, but most of the people you're going to be surrounded by, they're domain experts who had to learn to code to do what they're doing, but they didn't start with this. So they're going to rediscover some of the things I've talked about here, which is a good thing.
Good. Thank you. So one last question. Is that okay?
You may ask me as much as you wish. I am here to serve for the next 10 more minutes.
Good. So anyone in Zoom have another question? Else we have a few more questions on the side. Anyone want to ask live? No? Okay, so one thing that popped up really early on the meetup questions, and this is one we get a lot, and I would like to know your heuristics on. How does one know that when to stop experimenting? So you talked a lot about experimentation. So how does one know when to stop experimenting? What are your heuristics there?
Well, my short answer is you never stop experimenting. It's the degree of the scope of that experimentation that takes place. That I think the answer to the question is that I stop experimenting when I have a reasonable level of confidence that I have made the right set of significant design decisions. Experimentation will then move toward the edges and become incremental in nature. But at the point in time, my most important design decisions are relatively stable. That's when I can stop. And my experimentation moves outward.
Perfect. Thank you. Well, that wasn't 10 minutes. I have another quick one on YouTube. I think it's a quick one, but a really nice, interesting one. So Vedang asked, maybe basic question, but what advice would you give to computer science students on improving grip on architecture?
Great question.
Yeah.
Well, read the book, which eventually I'll finish writing. My long-suffering editor has been patient with me for about 15 years now. And I promised her I would finish this book before I die. So there you go. So there's that. I'd offer the following advice. Read other code. That you will learn a great deal by looking at the code of others and seeing how they have designed their systems. There's some great books on that topic. I'm going to do a plug for myself. Go to the site handbookofsoftwareengineering.com. That's one word. And you'll see a whole set of books there. It's an incomplete site. It's where I've sort of documented my major lectures and the like. So you'll see a few things in that space. So study the work of others, study other patterns. Go read Mary Shaw's book. You'll find a whole bunch of books there on architectural patterns and the like. And go study the fundamentals.
Perfect. Thank you. And thank you very much for today. We're gonna wrap off and close the YouTube stream, and then we can talk for a few more minutes after the stream went down.
I'll stay online so you and I can debrief. So thank you all for sticking with me. It's been fun. Stay safe, everyone.
Yeah, and thank you very much, Grady, for, well, this very wise and nice storytelling you did. And
thank you.
to the rest
My pleasure.
on stream, bye-bye. See you next time.